Section 5.4, Day 1 Sum and Difference Formulas. We're going to use the sum and difference formulas to evaluate trig functions and to verify identities. First question, is cosine of the quantity x plus 2 equivalent to cosine of x plus cosine of 2? So basically, can you distribute a trig function? So what I've done to kind of show you this is to graph each function on the graphing calculator, and you can see the differences between the two sides of the equation. So therefore, no, these are not equivalent trig equations. So if they are not equivalent, what does cosine of the quantity x plus 2 equal? Well, we have two formulas for the cosine of sum and difference as well, so one for each. So cosine of alpha plus beta is equivalent to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Not as easy as just distributing that trig function through. And if it's cosine of alpha minus beta, everything stays the same, except you can see that on the second equation you would be adding instead of subtracting. So if you add the two angles, you subtract those two products. If you subtract the two angles, you add those two products. So that's the difference between those two formulas. So let's take a look at our first example. Find the exact value of cosine of 105 degrees. We're going to use angles that we currently know the exact value for. So for example, pi over 6, we have the ordered pair square root of 3 over 2 comma 1/2. Remember, pi over 6 radians is equivalent to 30 degrees. Pi over 4 is our 45 degrees, and pi over 3 is 60 degrees. So those are the ordered pairs, and those are the values that we know. Obviously, we also know the ones in quadrant 2, 3, and 4 that have the same reference angle. So we can use any of those angles for any of the exact values that we're looking for. So I've also included all the other angles in radians of the entire unit circle for pi over 6, pi over 4, and pi over 3. So back to find the exact value of 105 degrees. Well, what angles are you going to add or subtract that we currently know to get cosine of 105 degrees? You actually have a couple options, but maybe the one that might stick out the most is to take cosine of 60 degrees and add 45 degrees. That would give you 105 degrees. So if we know those two angles, we can use the sum formula, and we know this is equivalent to cosine of 60 degrees times cosine of 45 minus sine of 60 degrees times sine of 45 degrees. Once you have the formula, now you're just going to evaluate what's cosine of 60 degrees. Remember, that is your x coordinate in the ordered pair. It is in quadrant 1. So you have 1/2 times cosine of 45. That's your x coordinate in the 45 degree ordered pair, square root of 2 over 2. Square root of 2 over 2 minus sine of 60. That's your y value. So that's square root of 3 over 2. And then sine of 45 is square root of 2 over 2. So we evaluate, we just multiply across. That would give us 1 times square root of 2, which is square root of 2. 2 times 2 is 4. Square root of 3 times square root of 2 is square root of 6. 2 times 2 is 4. We have a common denominator, so we can rewrite this as the square root of 2 minus the square root of 6 all over 4. So cosine of 105 degrees, its exact value is square root of 2 minus square root of 6 all divided by 4. And if you plug this in your calculator, you'll approximately get negative 0.259. And so think about it being negative. 105 degrees is in quadrant 2. So it should have a negative value. So that does make sense. Now, cosine of 60 degrees plus 45 gives you 105. Is there another way that you could rewrite 105 degrees? So think about that. Is there another way you could rewrite 105 degrees? Now, we would have to go outside of quadrant 1 to do that, but we could do 135 degrees minus 30 degrees. Those are, once again, two angles that we are familiar with that we could find. So do we get exactly the same answer that we got before? We should. We're just using different angles. We're using the difference formula now. But yeah, it should equal the same thing. And so there I went ahead and did it just to show you that you will get the order will switch around. You get negative square root of 6 plus square root of 2, but that's obviously equivalent to square root of 2 minus the square root of 6 all over 4. So it doesn't matter which angles you choose. These formulas work for all angles as long as they add or subtract up to 105 degrees. Also realize that since I did cosine, or the angle 135 degrees, cosine was negative square root of 2 because you are in quadrant 2. So you got to pay attention if you go outside of quadrant 1 what those angles are in terms of positive and negative. Also in another video I will prove the sum and difference formulas for cosine. Find the exact value of each expression. This goes back to my graph a little bit as to basically prove that these two things are not equivalent. So go ahead and use the sum formula for cosine to evaluate cosine of pi over 4 plus pi over 3, and then we'll also evaluate cosine of pi over 4 plus cosine of pi over 3, and obviously we will find out, because we looked at the graphs earlier, that these are not equivalent. So I'm going to go ahead and wait. You guys go ahead and pause, work through it, and I will do the same. So I went ahead and worked them out. The first one has to be done using the sum formula for cosine. I got square root of 2 minus square root of 6 over 4. And on the second one, I got square root of 2 plus 1 over 2. Definitely doesn't seem like they are the same value, even though they look different. Sometimes we have things that look different, but their values are the same. So I went ahead and calculated each of these just to make sure. So for the first one, we got negative 0.259. And for this one, when I approximated it, I got 1.2. So you can see that these are not equivalent values. Next is the sine, sum, and difference formulas. So you can look at these. We got sine of alpha plus beta is equal to sine of alpha times cosine of beta plus cosine of alpha sine of beta. And then when you have sine of alpha minus beta, it's the same thing, except then you are subtracting the two products. So example 3, find the exact value of sine of 165. So first, what two angles add or subtract to give you 165? So giving you a second to think, we could do sine of 120 degrees plus 45 degrees. We could also do sine of 135 degrees plus 30 degrees. Or we could do sine of 210 degrees minus 45 degrees. And there's more, but you could do any of these three or any of the other ones you find, as long as they add or subtract up to 165 and you're using angles that we currently know. So I'll go ahead and just use the first one here. So this would be sine of 120 degrees times cosine of the second angle, 45, plus cosine of 120 degrees, times sine of 45 degrees. And so once again, now we evaluate each of these. Remember, 120 degrees is in the second quadrant, so cosine of that will be negative, sine will be positive. 120 degrees has a reference angle of 60 degrees, so therefore sine of 60 degrees, remember your ordered pair, would be square root of 3 over 2. Cosine of 45, square root of 2 over 2. Cosine of 120, because you are in the second quadrant, is negative 1/2. And sine of 45 is square root of 2 over 2. Multiply those together, you get square root of 6 over 2 minus square root of 2 over 4. And so it's square root of 6 over 4, not 2. Which is equal to the square root of 6 minus the square root of 2 all over 4. So sine of 165 degrees is square root of 6 minus square root of 2 all over 4, which approximately is 0.259. It is in the second quadrant, sine should be positive. And on each of these, I do want the exact value. I'm just showing you the approximation so you can see whether it makes sense or not to the problem. On example 4, I've given you an expression, and I want you to write the expression as sine or cosine of the sum or difference of an angle. So look at this expression and compare that to your formulas, and which one does it match up with? It's cosine times cosine. So if you go back and look, cosine times cosine, that's not the sum and difference of sine, that's your sum and difference of cosine. And when it's being subtracted, you're actually adding the angles, and when you're adding, it's subtracting the angles. So let's go back and see which one it was. Cosine of 80 times cosine of 20 plus sine of 80 times sine of 20 would be equivalent to cosine of 80 degrees minus 20 degrees. And so that is cosine of 60 degrees. Find the exact value when you can, and we can. So cosine of 60 degrees is 1/2. So all of this simplifies down to 1/2. The last one we're going to look at is the tangent, sum, and difference formulas. You can see that these are a little bit more intense in terms of having the division and things like that. Let's go ahead and find the exact value of tangent of pi over 12. Now pi over 12, you know, that is, in terms of degrees, is 15 degrees. How can we get pi over 12? Well, you know 45 minus 30, 60 minus 45. So we can take pi over 3 minus pi over 4. That would be 60 minus 45. So that's what we'll use. We're going to do tangent of pi over 12 is equal to, and since we're subtracting, it will be tangent of pi over 3 minus tangent of pi over 4 all over 1 plus tangent pi over 3 times tangent pi over 4. Now we can take those and simplify. Tangent of pi over 3, that would be your 60 degrees, so that would be square root of 3, minus tangent of 45 would be 1. 1 plus square root of 3 times 1. So that will be square root of 3 minus 1 over 1 plus square root of 3. Now we are going to take this and simplify it a little bit, because we can multiply by its conjugate to get rid of the radical in the denominator. And so on top you'll get square root of 3 minus 1 plus square root of 3. Bottom you'll get 1 minus 3. So on top you'll have negative 4 plus 2 square roots of 3 when you combine your like terms. And then 1 minus 3 is negative 2. That will then simplify to 2 minus the square root of 3, because you're dividing both terms by negative 2. So therefore, tangent of pi over 12 is equivalent to 2 minus the square root of 3. And once again, don't forget about the summary. What was important about this? What are the takeaways from this section on sum and difference formulas?